According to the National Electrical Code, specifically the 2002 edition, it is not a code requirement to use a locknut first followed by a bushing when terminating conduit. The code does not mandate the use of locknuts alongside grounding bushings for securing conduit terminations. The primary requirement is that the bushing itself must be constructed of metal and properly listed for its intended purpose. National Electrical Code Article 300.4 addresses conduit bushings made entirely of insulating material. It specifies that these insulating bushings cannot be used to secure a fitting or raceway. However, this regulation does not extend to metal bushings such as the grounding bushings in question. National Electrical Code Article 300.20 provides further clarification regarding grounding bushings. It states that where threaded hubs or bosses on ferrous or non-ferrous metal raceways are used for the connection of soft metal conduits, grounding bushings shall be installed prior to assembly of the raceway. This section focuses on situations where soft metal conduits are connected to metal raceways using threaded hubs or bosses. It mandates the use of grounding bushings in these scenarios, but it does not specify the need for locknuts to be used with the grounding bushings. It's important to understand the function of each component. A locknut's main purpose is to mechanically secure the conduit to the enclosure, ensuring a tight and stable connection. This helps prevent the conduit from loosening over time due to vibration or other factors. A grounding bushing, on the other hand, serves to provide a reliable path for ground fault current. It ensures that the conduit is properly bonded to the enclosure, allowing any fault current to safely return to the source. While locknuts are not explicitly required by the National Electrical Code in conjunction with grounding bushings, their use is a common and often recommended practice. Using both a locknut and a grounding bushing provides a more robust and secure connection, offering both mechanical stability and a reliable grounding path. Many electricians choose to use both components as a matter of best practice, even though it is not strictly mandated by the code. The code emphasizes that grounding bushings must be made of metal and listed for their intended purpose, ensuring they can effectively carry fault current. When connecting soft metal conduits to metal raceways with threaded hubs or bosses, grounding bushings are essential for maintaining a proper ground. Ultimately, while the National Electrical Code does not explicitly require the use of locknuts with grounding bushings, it's crucial to ensure that all electrical connections are made safely and securely, adhering to the relevant code requirements and industry best practices. This is about ensuring electrical safety and preventing potential hazards. Now let's delve deeper into grounding and bonding concepts in electrical systems. Grounding and bonding are critical for electrical safety. Grounding provides a low impedance path for fault current to return to the source, while bonding ensures that all metal parts of an electrical system are at the same potential. The National Electrical Code outlines specific requirements for grounding and bonding to protect people and equipment from electrical shock and fire hazards. Grounding refers to connecting an electrical system to the earth. This connection provides a reference point for voltage and helps to stabilize the system. A grounding electrode, such as a ground rod or metal water pipe, is used to make this connection. The grounding electrode conductor connects the grounding electrode to the system's neutral point, typically at the service entrance. Bonding involves connecting all metal parts of an electrical system together to create a continuous conductive path. This includes metal conduits, enclosures, equipment frames, and other non-current carrying metal parts. Bonding ensures that if a fault occurs, the fault current will have a low impedance path to return to the source, tripping the circuit breaker or fuse and energizing the circuit. The main bonding jumper is a conductor that connects the grounded conductor neutral to the equipment grounding conductor at the service entrance. This connection creates a common point for grounding and bonding, ensuring that all metal parts of the system are at the same potential. Equipment grounding conductors are used to connect the non-current carrying metal parts of equipment to the grounding system. These conductors provide a path for fault current to return to the source, protecting people and equipment from electrical shock. Sizing grounding and bonding conductors is crucial for ensuring their effectiveness. The National Electrical Code provides tables and guidelines for sizing these conductors based on the size of the overcurrent protection device in the circuit. Undersized grounding and bonding conductors can limit the flow of fault current, delaying the tripping of the circuit breaker or fuse and increasing the risk of electrical shock. Proper installation of grounding and bonding conductors is also essential. These conductors must be securely connected to the grounding electrode, equipment frames, and other metal parts of the system. Loose or corroded connections can increase impedance and reduce the effectiveness of the grounding and bonding system. Regular inspection and maintenance of grounding and bonding systems are necessary to ensure their continued effectiveness. Connections should be checked for tightness and corrosion, and grounding electrodes should be tested to verify their resistance to earth. Now let's discuss some common misconceptions about grounding and bonding. One common misconception is that grounding is only necessary for safety. While safety is a primary concern, grounding also plays a role in system performance and stability. Grounding helps to reduce voltage fluctuations and noise, improving the reliability of electrical equipment. Another misconception is that bonding is only necessary for metal parts. Bonding is also important for non-metallic parts that may become energized due to a fault. For example, plastic enclosures may contain metal components that need to be bonded to the grounding system. A third misconception is that a ground rod is all that is needed for effective grounding. While a ground rod is an important part of the grounding system, it is not sufficient on its own. The grounding system must also include bonding conductors and equipment grounding conductors to provide a complete and effective path for fault current. In summary, grounding and bonding are essential for electrical safety and system performance. The National Electrical Code provides specific requirements for grounding and bonding to protect people and equipment from electrical shock and fire hazards. Proper sizing, installation, and maintenance of grounding and bonding conductors are crucial for ensuring their effectiveness. Understanding the principles of grounding and bonding is essential for all electrical professionals. Let's explore the practical aspects of conduit installation. When installing conduits, it is important to consider several factors to ensure a safe and reliable electrical system. These factors include conduit type, size, support, and termination. There are several types of conduits commonly used in electrical installations, each with its own advantages and disadvantages. Rigid metal conduit, often called RMC, is a heavy-duty conduit made of steel or aluminum. It provides excellent protection for conductors and is suitable for both indoor and outdoor applications. Intermediate metal conduit, often called IMC, is a lighter weight version of rigid metal conduit. It offers similar protection to RMC but is easier to work with and less expensive. Electrical metallic tubing, often called EMT, is a thin-walled conduit made of steel or aluminum. It is commonly used for indoor applications and is easy to bend and cut. Flexible metal conduit, often called FMC, is a flexible conduit made of steel or aluminum. It is used for connecting equipment that may be subject to movement or vibration. Liquidite flexible metal conduit, often called LFMC, is a flexible conduit with a liquidite jacket. It is used in wet or damp locations to protect conductors from moisture. The size of the conduit must be appropriate for the number and size of conductors being installed. The National Electrical Code provides tables that specify the maximum number of conductors allowed in each size of conduit. It is important to follow these guidelines to prevent overheating and damage to the conductors. Conduits must be properly supported to prevent sagging and damage. The National Electrical Code specifies the maximum spacing between conduit supports based on the type and size of the conduit. Support should be securely fastened to the building structure and should not damage the conduit. Conduit terminations must be made properly to ensure a secure and reliable connection. Fittings such as couplings, connectors, and bushings are used to terminate conduits. These fittings must be listed for use with the type of conduit being installed and must be properly tightened to ensure a good electrical connection. When installing conduits in wet or damp locations, it is important to use liquid-tight fittings and seal the conduit ends to prevent moisture from entering. This will help to protect the conductors from corrosion and damage. Bending conduits is often necessary to route them around obstacles. Conduit benders are used to create smooth, even bends without damaging the conduit. It is important to follow the manufacturer's instructions when using a conduit bender to ensure that the bends are made correctly. When cutting conduits, it is important to use the proper cutting tool to create a clean, square cut. This will ensure that the conduit fits properly into the fittings and that there are no sharp edges that could damage the conductors. After cutting conduits, it is important to ream the cut ends to remove any burrs or sharp edges. This will prevent damage to the conductors as they are pulled through the conduit. When pulling conductors through conduits, it is important to use a pulling lubricant to reduce friction. This will make it easier to pull the conductors and prevent damage to the insulation. It is also important to avoid overfilling the conduit, as this can make it difficult to pull the conductors and can cause overheating. Proper grounding and bonding of conduits are essential for electrical safety. Metal conduits must be bonded to the grounding system to provide a path for fault current to return to the source. This can be accomplished by using grounding bushings and bonding jumpers. In summary, proper conduit installation is essential for a safe and reliable electrical system. It is important to consider conduit type, size, support, and termination when installing conduits. Following the National Electrical Code guidelines and industry best practices will help to ensure that the electrical system is installed correctly and safely. Let's discuss working with electrical boxes. Electrical boxes are essential components of an electrical system, providing a safe and secure enclosure for wiring connections and devices. There are several types of electrical boxes commonly used in electrical installations, each with its own purpose. Outlet boxes are used to house receptacles, switches, and other devices. They are typically mounted in walls or ceilings and are available in various sizes and shapes. Junction boxes are used to provide a location for splicing or terminating conductors. They are typically used when extending or modifying existing circuits. Pull boxes are used to provide access to conductors for pulling or feeding them through conduits. They are typically larger than outlet boxes or junction boxes and are often used in long conduit runs. Device boxes are designed to accommodate specific types of devices, such as ceiling fans or smoke detectors. They typically have mounting brackets or other features that make it easier to install the device. The size of the electrical box must be appropriate for the number and size of conductors and devices being installed. The National Electrical Code provides guidelines for calculating the minimum box size required for each type of installation. Overfilling an electrical box can lead to overheating and damage to the conductors and devices. Electrical boxes must be properly supported to prevent them from falling or becoming damaged. Outlet boxes and device boxes are typically supported by the wall or ceiling structure, while junction boxes and pull boxes may require additional support. Electrical boxes must be securely fastened to the supporting structure using screws, nails, or other appropriate fasteners. When installing electrical boxes, it is important to ensure that they are properly aligned and level. This will make it easier to install devices and will improve the overall appearance of the installation. When cutting openings for electrical boxes in walls or ceilings, it is important to use a proper cutting tool to create a clean, square cut. This will ensure that the box fits properly and that there are no gaps or sharp edges. When installing conductors in electrical boxes, it is important to leave enough slack to allow for easy connection to devices. The National Electrical Code specifies the minimum length of conductor that must be left in the box. When making connections in electrical boxes, it is important to use proper wiring methods and connectors. Wire connectors must be listed for use with the type of conductor being installed and must be properly tightened to ensure a good electrical connection. When installing devices in electrical boxes, it is important to follow the manufacturer's instructions and to ensure that the devices are properly grounded. Grounding screws are typically provided on devices for connecting the equipment grounding conductor. When closing up electrical boxes, it is important to ensure that all conductors and devices are properly positioned and that the box cover is securely fastened. Loose or improperly positioned conductors can lead to short circuits and other problems. In summary, proper installation of electrical boxes is essential for a safe and reliable electrical system. It is important to consider box type, size, support, and wiring methods when installing electrical boxes. Following the National Electrical Code guidelines and industry best practices will help to ensure that the electrical system is installed correctly and safely. Now let's shift focus to understanding overcurrent protection. Overcurrent protection is a critical aspect of electrical safety, designed to protect electrical circuits and equipment from damage caused by excessive current flow. Overcurrent can result from short circuits, overloads, or ground faults. Overcurrent protection devices, such as circuit breakers and fuses, are designed to interrupt the flow of current when it exceeds a safe level. Circuit breakers are electromechanical devices that automatically interrupt the flow of current when an overcurrent condition is detected. They can be reset manually after the fault has been cleared. Fuses are single-use devices that interrupt the flow of current by melting a fusible link when an overcurrent condition occurs. They must be replaced after they have blown. There are several types of circuit breakers and fuses available, each with its own characteristics and applications. Thermal circuit breakers use a bimetallic strip that bends when heated by excessive current, tripping the breaker. Magnetic circuit breakers use an electromagnet that trips the breaker when the current exceeds a set level. Time delay fuses are designed to allow short-duration overloads to pass without blowing, while still providing protection against sustained overcurrent. Current-limiting fuses are designed to quickly interrupt the flow of current during a short circuit, limiting the amount of energy that is released into the circuit. The size of the overcurrent protection device must be appropriate for the ampacity of the circuit conductors and the equipment being protected. The National Electrical Code provides guidelines for selecting the correct size of overcurrent protection device for various applications. Undersized overcurrent protection devices will trip prematurely, while oversized devices will not provide adequate protection against overcurrent. Overcurrent protection devices must be installed in readily accessible locations and must be protected from physical damage. They must also be properly labeled to indicate the circuit they protect and their ampacity rating. Regular testing and maintenance of overcurrent protection devices are necessary to ensure their continued effectiveness. Circuit breakers should be periodically tested to verify that they trip at the correct current level. Fuses should be inspected for signs of damage or deterioration. When replacing overcurrent protection devices, it is important to use the correct type and size. Using the wrong type or size of overcurrent protection device can create a safety hazard and can damage electrical equipment. It is also important to ensure that the replacement device is listed for use in the application. In summary, overcurrent protection is essential for electrical safety. Circuit breakers and fuses are used to interrupt the flow of current when it exceeds a safe level. Proper selection, installation, and maintenance of overcurrent protection devices are crucial for ensuring the safety and reliability of electrical systems. Now, let's explore electrical safety practices. Electrical safety is paramount in any electrical work environment. Adhering to established safety practices is crucial to prevent electrical shocks, burns, fires, and other hazards. Before commencing any electrical work, it is essential to de-energize the circuit or equipment being worked on. This involves turning off the power at the source, such as a circuit breaker or disconnect switch. Once the circuit is de-energized, it is important to verify that the power is off using a voltage tester. A voltage tester should be used to check all conductors and terminals to ensure that no voltage is present. Lockout/tagout procedures should be followed to prevent accidental re-energization of the circuit. This involves placing a lock and tag on the disconnect switch or circuit breaker to indicate that the circuit is being worked on. Personal protective equipment, often called PPE, should be worn when performing electrical work. This includes safety glasses, rubber gloves, and insulated tools. Safety glasses protect the eyes from arc flash and flying debris, while rubber gloves and insulated tools protect against electrical shock. Never work on live electrical circuits unless absolutely necessary. If live work is unavoidable, special precautions must be taken, such as using insulated tools and wearing appropriate PPE. Maintain a safe working distance from energized parts. The distance depends on the voltage of the circuit. The higher the voltage, the greater the required working distance. Be aware of your surroundings and avoid contact with grounded objects while working on electrical circuits. Contact with grounded objects can create a path for current to flow through your body, resulting in electrical shock. Use only approved and properly maintained tools and equipment. Damaged or improperly maintained tools can create a safety hazard. Inspect tools and equipment before each use to ensure that they are in good working condition. Follow all applicable codes and standards such as the National Electrical Code and Occupational Safety and Health Administration, often called OSHA, regulations. These codes and standards provide guidelines for safe electrical work practices. Be aware of the potential hazards associated with electrical work, such as arc flash, electrical shock, and explosions. Take steps to mitigate these hazards by following established safety practices and using appropriate PPE. If you are not qualified to perform electrical work, do not attempt it. Electrical work should only be performed by qualified and trained personnel. Report any unsafe conditions or practices to your supervisor or safety officer. It is important to address potential hazards before they lead to accidents. In summary, electrical safety is paramount in any electrical work environment. Adhering to established safety practices, using appropriate PPE, and following applicable codes and standards are crucial for preventing electrical accidents. Staying vigilant and prioritizing safety can help to ensure a safe working environment for yourself and others.